All right, guys, it's finally time to do your Amali exam. So this video, we're going to discuss this experiment, heat of displacement. Okay, so heat of displacement in the textbook is actually an activity, right? It's not an experiment. So that's why in the textbook, you won't see any variables. Okay, but today I'm going to make this into um, an experiment. So I'm going to give you the variables as well. If they ask this question, right? If it comes out, I mean, in this experiment, if it comes out, how to treat it like an experiment. Okay, so look at the aim. So the question will come something like, this is an experiment to determine and compare. You just follow the aim lah, to determine and compare heat of displacement of copper from copper to sulfate with zinc metal and magnesium metal. So there'll be two different metals, two or more. Okay, two or more different metals. So the first thing we want to do whenever we are attempting the Amali question, the first thing you want to do is to identify MV and RV. Most of the experiment is going to depend on this, the manipulated variable and the responding variable. Okay, so most of the time we can get it based on the question itself. All right, so based on the statement, based on the aim here, you can see, why don't you pause and try to identify MV and RV first? Just give yourself about 1 minute. Okay, so the manipulated variable here will be, look at what we are changing at the beginning of the experiment. Okay, we are using two types of metal, isn't it? We are using zinc and magnesium. So these are the two types of metals that we use to get, and then at the end, we are going to compare the heat of displacement. All right. So therefore, what we do in the beginning, what we change in the beginning is the manipulated variable. The outcome as a result of what we change is the responding variable. Okay. So the responding variable here will be heat of displacement. Now, even though heat of displacement is not an experiment, okay, there are other experiments in this chapter. So if you follow that, especially heat of neutralization, okay, heat of neutralization has experiment, not activity. So heat of neutralization, you can see in the textbook, the RV that they use is actually heat of neutralization. It is not anything, it is not like, for example, the increase in temperature or the increase in the thermometer reading. No. Okay, they use heat of neutralization. So following that pattern, in this experiment, the responding variable will be heat of displacement. Okay, right? Okay, so what is fixed then? What is the same? When we use zinc and copper, I mean, zinc and magnesium, what are we not changing? Even that we can get directly from here, isn't it? Because we are going to use, the solution that we're going to use is still copper to sulfate, whether we are using zinc or magnesium. In both cases, we use copper to sulfate. Okay, so this will be fixed. Now, whenever you have a solution that is the fixed variable, always use volume and concentration. Give both volume and concentration of whatever solution. So in this case, it will be volume and concentration of copper to sulfate solution. All right. So this is just an example here. You can see this manipulated variable here. Now, if you're not sure about what to put manipulated variable, if you're not sure about the classification, okay, that means, let's say you wanted to put type of metal, okay, but you're not sure because you're using magnesium and zinc, right? You can write your manipulated variable in this manner. You can write both, or if there's more than two, write everything. The most important thing is you have to use N. Don't use all. Okay. So in this case, first one we're using magnesium, then we are switching with zinc, right? So you can say magnesium powder and zinc powder as the manipulated variable, no problem. Okay, all right. Okay, if you don't want to take the risk, for example, if you don't know type of metal is going to be accepted or not, just give this, it will be accepted. It should be accepted, right? Okay, then we have responding variable is just the heat of displacement. Okay, fixed variable, volume and concentration of the copper to sulfate solution. Okay, so these are the variables. Now this is very important because we are going to use this for for the operational definition. For operational definition, for hypothesis, okay, for your conclusion, all right. Many things rely on this. Your tabulation of your results, everything relies on MVRV usually. So MVRV is the first thing you need to identify. Okay, once you've got that, okay, let's go on. So drawing the setup, draw the apparatus setup for this experiment. Now, they can ask you to draw for Amali. In fact, it has come out before for bio. Okay, they asked to do the experiment. They asked to draw the apparatus setup. That was the considered the unguided bio paper. It has come out before for SPM. Okay, so just make sure you know how to draw the apparatus setup. This is very simple. All your thermochemistry experiments are very simple, except for heat of combustion is a bit complicated. But heat of displacement is no problem because everything is done in a polystyrene cup, isn't it? Okay, we're not even going to use a beaker. So again, why don't you pause it here and try to draw, see whether you can draw the setup. Okay, now this is the setup. Very simple. All right, so we have the copper 2 sulfate solution in a polystyrene cup. Make sure it's a polystyrene cup. Okay, anyway, the apparatus given to you should have the polystyrene cup. All right, and then we have thermometer. It should be in the copper 2 sulfate solution, dipped into copper 2 sulfate solution. Okay, and then this is the magnesium powder that we're going to add. That's it. That's it. All right. Okay, so here you can see we have two polystyrene cups. Two polystyrene cups is for insulation, extra insulation. So the cup will be stacked like that. So what is happening here is that when we have that extra cup, you actually have a pocket of trapped air. Okay, you have a pocket of trapped air, which then acts as a insulator. So it prevents heat loss to the surrounding. Here, the pocket of trapped air will be here. So that's two cups. Okay, this can be a precautionary step as well if it's not already given. It can be a precautionary step to prevent heat loss to the surrounding. Okay, first let's tackle operational definition. So operational definition for chemistry is the clearest. We have the most examples and the most consistent examples in all the mark schemes. So I hope you know, but if not, don't worry. The format is very simple. For operational definition for chemistry, you need to have two things. What is observed and what is done. Okay. The format that I teach my students is what is observed in one sentence. What is observed? When? What is done? This is the format that I ask my students to use. Okay. Now, what's important here is the what is observed must be a, a reading that we get from the experiment. Okay, it must be the reading. For example, the increase in the thermometer reading, the actual reading that we get, not the value, but the type of reading that we get. Okay, so don't use theory. Operational definition, do not use theory. Everything must be practical. Okay, so what we have done in the practical. So what is observed here is basically the responding variable which we measure. Or in some cases, when the responding variable is qualitative, that means there's no value to it, what we observe. But it must be what we collected, the data that we collected during the experiment. Okay, so in this particular case, what is observed? All right, okay. So in this experiment, all right, let's look at the procedure to understand what is observed and what is done. So first we measure 50 cm cube or 0.5 mole per dm cube copper to sulfate solution. Okay, and then we pour into each polystyrene cup. Okay, so here we have two cups because we are going to do the displacement with two metals. So we have two cups. Okay, this double cup is a different thing. So this is the additional precaution. These two cups is not for the double cup. Okay, these two cups is because we have two metals. Okay, now then we place a thermometer in each polystyrene cup and record the initial temperature after 2 minutes. Okay, this is important. We have to record the initial temperature after 2 minutes. Later, I have some discussion questions to go through with you all. Okay, so we'll look at the discussion questions later. I will answer. I will explain why we do this and all that. Okay, then we add the magnesium powder into one of the polystyrene cups until in excess. All right, how will we know when it's in excess? When it doesn't dissolve anymore. When the magnesium powder doesn't dissolve anymore, then it is in excess. Okay, then cover the polystyrene cup and stir using a thermometer. Okay, record the highest temperature. Record the highest temperature of the mixture. Notice it's not final temperature. It's not final temperature. It's highest temperature. Okay, because you don't know what the final temperature is going to be. All right, so repeat steps 1 to 4 by replacing the magnesium powder with zinc powder. That's all. Okay, so when we look at this procedure, right, what is observed? What are we actually measuring or observing for the responding variable? Okay, so basically we are getting the highest temperature. That's what we are actually measuring for the responding variable. For the heat of displacement, we are getting the highest temperature. Okay, but this one you can't just use the highest temperature, isn't it? You have to use the change in temperature, right? If you want heat of displacement, because heat of displacement will be delta H is mc delta theta over n, right? So we need delta theta. So here they have given the operational definition in your textbook for the other heat of reaction also lah. So if we follow that format, the observed RV here will be the change in the thermometer reading, the increase in the thermometer reading. Okay, the increase in the thermometer reading. So that is the observed RV, right? Okay, so you cannot use heat of displacement here, cannot, right? We have to use the increase in the thermometer reading. Okay, so what is done? What did we do to get this observation? All right, to get this responding variable, to get this measurement, what is done for this? So when we do what? When we add magnesium powder into 50 cm cube of 0.5 mole per dm cube copper 2 sulfate solution until excess. That is done. Okay, so when we do this, then we get this observation. That is operational definition for chemistry. Very, very uniform. Okay, all the mark schemes you can see, they have the same format for chemistry, which is something we don't have for the rest. All right. Okay, so example of operational definition here. So this is based off what the other operational definitions are in the textbook. Okay, we don't have one for heat of displacement, but based on the others, operational definition for heat of displacement, this is my sample answer. So when magnesium powder is added to copper 2 sulfate solution until in excess. So this is the what is done with. When what is done, the order doesn't matter. Okay. When what is done, when magnesium powder is added to copper 2 sulfate solution until in excess. Right? Okay, this is the additional bit. This is the additional bit that's there for the other operational definitions. Okay, the second line is to produce 1 mole of copper metal. Copper is the one that's displayed. Okay, to produce 1 mole of copper metal. So this is what is done. This extra bit, again, I'm basing it off the other examples that we have for the other heats of reaction in the textbook. Okay, to produce 1 mole of copper metal, what is observed? The thermometer reading increases. Don't say temperature. Don't say temperature. Again, it must be the actual reading that we are using for the responding variable. So the thermometer reading increases. Okay, this will be my example for the operational definition for heat of displacement. All right. Okay, now let's say you get an unguided paper, meaning they don't give you the procedure, they ask you to write the procedure. Now, for chemistry, whatever format they ask you the question, okay, whether it's um, your procedure should include methods of handling the variable and the precaution. Sometimes they ask like that, method of handling variable and the precautionary steps. That's it. Okay, or they ask you to just write the procedure for the experiment. Okay, if you look at this year's trial papers, both have come out, both types have come out, but for chemistry, it doesn't matter. You write the full procedure anyway. Please remember, because it's not the same for physics. It's not the same for physics. Okay, for chemistry, whatever it is, just write the full procedure. Okay, so when you write the full procedure, there's some things you need to take note of. You have to mention all the volume and concentrations. Okay, whenever we are using solution. If we are using solids, then mention the mass, unless it's excess. So for example, in this experiment, we are adding magnesium powder. This is a solid, but in excess. So you don't need to mention the mass. Okay, otherwise you need to mention the mass. Right? So mass, the volume, the concentration, all must be there. Whenever you can, you mention the measuring instruments just to be safe. So for example, measure 50 cm cube of 0.5 mole per dm cube copper to sulfate solution using a measuring cylinder and pour into each polystyrene cup. For example, it's better for you to include it just in case. Okay. All right. Okay. Then repeat. The last line is usually repeat. The last step is usually repeat. Repeat steps one until however many you have by replacing the MVs. All right. Okay. So that's it. This is the experiment. And the experiment itself is simple. Now look at the types of questions that can come up. Okay, so, oh, sorry, before we go to discussion, the results. How do you present the results here? So again, based off the examples, we can use this. This is not given in your textbook. Okay, so will be my sample. You have to read the procedure carefully if it's given to you. Right? When it comes to the results table, you must include MV. MV must be here. Usually it's the first column. Here is the metal, magnesium and zinc. Okay, first one. And then you must have RV. Okay, MV and RV must be there. However, it's not limited to just MV and RV. You have to check and see, is there anything that is that the procedure asks us to record? Anything that they ask you to record must be in the table. Okay, must be in the table. All right. So, okay, you see here. Let's see. You see, you can see here. Record the temperature of the solution after 2 minutes. So the moment you see record, put it in the table. Okay. Then here, record the highest temperature. Okay. You see record, put it in the table. Put it in the table. All right. Okay. Just take note on this lah. You can use the procedure to guide you if you're not sure what header to use. Okay. MV, RV, anything that you need to record. That's all. MV, RV, anything you need to record. Okay. Okay. So when we look at this, then we have initial temperature, highest temperature. Highest, again, not final, highest, highest temperature of the mixture. Okay. Make sure your units are here, degrees Celsius. And then we have the change in temperature, delta theta, degrees Celsius. Okay. So this is my sample. Again, this is my sample. Please read the procedure carefully. Read the procedure carefully. Okay. Now let's answer some questions. So these are the common questions. Write the chemical and ionic equations. Right. The chemical and the ionic equations for the displacement of copper from copper to sulfate solution with magnesium metal. Okay, pause and try. All right. So the chemical equation here will be displacement of copper from copper to sulfate solution. So the reactant here is the copper to sulfate solution, right? With the magnesium metal. Okay. So magnesium and copper to sulfate. Now what's going to happen? Magnesium is more electropositive than copper. Okay. So magnesium is going to displace copper. Magnesium will displace the copper from the copper to sulfate solution. So we get magnesium sulfate solution instead. That's all. It's already balanced. It's already balanced. Please don't forget to balance your equations. Okay, next. Ionic equation. So what are the spectator ions here? Which are the spectator ions? Now, this is an aqueous solution, copper to sulfate and magnesium sulfate. These are your aqueous solutions. Okay. So aqueous solution here, we have the copper 2 ion and the sulfate ion. After the reaction, we have magnesium ion and the sulfate ion. So which is the spectator here? Sulfate. Sulfate is the spectator because it has not changed chemically before and after the reaction. It did not take part in the reaction. Therefore, it's a spectator. So what's left? Copper 2 ion, copper 2 plus magnesium solid. Okay, then we have product magnesium ion, copper solid. That's your ionic equation. Okay, so here we go. Ionic equation. Right? Okay, so do the same. Number 2, look at number 2. Do the same for zinc. Write the chemical and ionic equation. Where is my... Okay. Chemical and ionic equation for the displacement of copper from copper to sulfate with zinc metal. Okay, pause and try. Okay, same story, Same story. This time is zinc. Zinc will displace copper because zinc is more electropositive. Okay, sulfate is the spectator again. Sulfate is gone. Everything is already balanced. All right. Okay, now look at number 3. Is the heat of displacement of copper by zinc or magnesium higher? Which is higher? Explain. Zinc or magnesium? So, which will be higher? It depends on which is more electropositive, right? Okay, the more electropositive the metal, the higher the heat of displacement. Okay, so which is higher, zinc or magnesium? Magnesium. Magnesium. Okay, you need to know based on your, you can refer to your, it's not the same thing, but you can refer to your reactivity series of metal. Okay, usually the position is the same. When we compare electropositivity and reactivity, usually the position is the same. Okay, technically it's not the same thing. Okay, but you can use that as a reference. So magnesium is higher than zinc, isn't it, in reactivity series? Okay, so the answer is magnesium. And the reason is magnesium is more electropositive than zinc. Okay. All right. Now, state 2 observations other than change in temperature. Okay, why don't you pause and try? All right. So, which is it? So, in this experiment, whenever you have an experiment that involves copper 2 sulfate, you will already have extra observations. Because copper 2 sulfate is a blue color solution, right? So, if you look just based off the ionic equations, you can see very clearly here. Copper 2 ion is blue. Okay. So, if you add magnesium until excess, that means all the copper 2 ions will be used up in the reaction, right? which means one of the observations will be, remember, observations, you must give the starting and the ending. Don't just give the ending. So you must say blue color solution becomes colorless. Blue solution turns colorless. Okay, that is one. Number two, copper metal is formed. Now, copper metal has a characteristic color, isn't it? What's the color of copper metal? Brown. Brown. So we can say brown solid is formed. Right? Okay. Okay. So solution turns from blue to colorless, brown precipitate is formed. Right? Okay, state the reason for using both metals in excess. Why do we use the metals in excess? I think I've already given you the answer. Not I think, I have already given you the answer earlier, isn't it? Why do we use the metals in excess? To ensure that whenever we use any reactant in excess, the reason is so that the other reactant will be completely used up, right? Okay, there will be none left. So we want to make sure that there's no more copper 2 ions in the copper 2 sulfate solution. That's why we use the metals in excess, right? So how do you write the answer here? So this is my sample answer. All these are my sample answers. Okay. So my sample answer will be to ensure that all the copper 2 ions have been displaced completely. All the copper 2 ions. Okay. All right. Now, let's look at number 6. So they can ask you this as well. Okay. So given the heat of displacement of copper 2 sulfate is negative x kilojoule per mole with magnesium, and then negative y kilojoule per mole with magnesium. Okay, with zinc is negative x kilojoule per mole, with magnesium is negative y kilojoule per mole. Draw energy level diagram for both reactions. Okay, so first of all, if you are required to do calculation for your heat of displacement, okay, make sure your calculation you include the sign. Please include the sign. So your calculation for heat of displacement will be delta H is mc delta theta over n. Okay, so this mass will be the mass of the solution. So that means the copper 2 sulfate solution. So for example, in this experiment, we use 50 cm cube, isn't it? Right? Here we use 50 cm cube. So they should give you the density, or if not, you can assume the density 1 gram is to 1 centimeter cube. 1 gram, 1 centimeter cube. So 50 centimeter cube is to 50 grams. All right? So you use here 50. Okay? Because your C will be in joules per gram. Joules per gram. Okay? So it will be 4,200 joules per gram. Okay, and then your delta theta. So whatever it is, use your delta theta here, use positive value for delta theta. Okay, because we only want the magnitude of heat change. Okay, so theta 2 minus theta 1. Okay, and then N will be the number of moles of copper displaced. So moles of copper, right? Okay, since magnesium is in excess, okay, so let me teach you how to calculate here. Now, the whole thing will be wrong if you don't put negative here. Don't forget to add the negative. This is actually what I wanted to stress just now. Don't forget to add the negative. Okay, all right. As long as it's exothermic, temperature should go up. Okay, temperature should increase. If temperature increases, exothermic, therefore put a negative. That's all. Okay. Okay, moles of copper, how to calculate? So you have to go back to your equation. So let's say we are doing the magnesium, magnesium and copper 2 sulfate. So we get copper and magnesium sulfate, right? Now, the moles here should be this, moles of copper. But of course, we don't have moles of copper directly. What we have is the moles of copper 2 sulfate because we have the volume and we have the concentration. All right. So the concentration will be, oh, class, this should, guys, this should be 4.2. It depends on the unit, lah, right? But usually in chemistry, we use 4.2 because it is gram per gram. Okay. Okay. Anyway, don't worry about that. Just use whatever value they give. They will provide the value. Okay. So let's go back to the procedure. We are using 50 cm cube, 0.5 mole per dm cube, right? Okay. From here, we use mv per thousand. We use mv per thousand. We can get the number of moles of copper 2 sulfate. So the number of moles of copper 2 sulfate, will be mv per thousand. So molarity 0.5, V 50, volume per thousand. Okay, so that will be 0.025. 25 divided by 1000 moles. So you can use the mole ratio here, 1 to 1. Okay, so moles of copper 2 sulfate to moles of copper is 1 to 1. Therefore, number of moles of copper will be the same as the number of moles of copper 2 sulfate, which is 0.025 moles. Okay, this one you can use here, here, right? However, the answer that you will get here will be in joules. So let's say um, negative P joules, joule per mole. Don't leave your answer in joule per mole. Heat of reaction, we always give kilojoule per mole. So what do? Divide by 1000. So it will be negative P over 1000 kilojoule per mole. This is the calculation. This is the calculation for heat of displacement. Okay. All right. So now let's go back to this. Draw the energy level diagram. So do you remember how to draw energy level diagram? If you do, pause and try. Okay. So let's look at this. So energy level diagram, they ask you to draw for both. So what are the components for your energy level diagram? So we only have one axis, vertical axis, energy. Okay, energy. Now remember this is an exothermic reaction, which means energy level of the reactant must be higher than the product. Both, okay. Now when you write the reaction, when you write the reactant side and the product side, make sure you use the physical states as well. Use the physical states as well. Okay. And then your arrow head must be here, down. There must be an arrowhead. And you must label data H here. Don't forget the negative. Again, please do not forget the negative. All right. You can use the chemical equation. You can use ionic equation. Both are fine. Both are fine. However, if they ask you to draw both, you must clearly show the magnesium is more than zinc. The magnitude. That means this arrow must be longer for magnesium compared to zinc. Okay. All right. So guys, please be prepared for unguided also lah. However unlikely it may be, just be prepared. Okay, these are generally the techniques and the formats lah. Please remember your operational definition format. All right. Okay, guys. All the best to y'all. I'll see y'all in the bio video.